Good afternoon. Can anyone give me a thumbs up if you can hear me well? That'd be appreciated. Thank you. Thank you guys. We'll start here in a minute.
You mind reminding me when the day of the midterm is?
Yes, I'm gonna speak about it now. Okay, so let's go ahead and begin. That is sharing and it's recording. Okay, that's good. So, to speak a little bit course logistics before we dive into our lecture, um, I announced about this and I just wanted to remind the students about it again, about Hack at UCF. I know some of our students are in class, are enrolled in that community, but it's highly recommended that you join that community as they discuss various topics regarding networking, security, privacy, and it's a very cool program. The membership is not expensive; it's only $10 per semester, and they meet every Friday, I think, and there's like free pizza that is supplied. So it is an idea that you can get general experience from, make friendship, make connections, develop yourself with hands-on skills and many more things. Okay, so that is for the announcement. I want to speak a little bit of where we are in the class. So currently we're in week 8, and we're going to cover TCP as a protocol itself. Then on Wednesday, we're going to cover congestion control. And then next week, we'll have TCP congestion control. And then next Wednesday, there won't be any class that'll be used for you guys to review. And then our midterm is looking like that's going to be on the 20th of October. And it's going to open that Monday and will be due the same day on Monday. So you'll see questions related or similar to how the homework comes in, those related questions, and you'll submit a report similar to the homework. And then after that, we'll pick up where we left off in the modules. Does that make sense? Okay. How was the programming assignment? Was it balanced? Good? Okay. Yeah. So, okay, so we can go ahead and start. So last week we left off and we spoke about the RDT, reliable data protocol or channel and the essence. And I just want to give a quick reminder or a recap of this and where we left off and where we're going to pick up. So the last where we left off in the last lecture is when we talked about UDP and its limitations. Basically, this is the outline that we are going to be using throughout TCP and UDP. We are trying to get a message from the application to the sender. We talked about multiplexing, demultiplexing. We talked about UDP as a protocol. We transferred from UDP as its limitation, and we talked about reliable data control as a protocol itself. And then today we will speak about TCP. So we talked about finite state machines and how there's two states, and then when there's two states, an event happens and an action gets taken that makes the state change its place. We talked about these abstractions that are used within the protocol to send and receive data, which is from the server, receiver, or sender side that we did talk about. And we said that RDT 1.0 is the first version of RDT. And here we are assuming that it is a reliable transfer over a reliable channel. And this is like imagining that, oh, we take the case scenarios of everything is perfect. Then we said that there's limitations with RDT1, and it's that the real networks are unreliable and we cannot detect or cover from the errors or loss. So we moved on RDT 2.0 and we've seen many things and we tested each scenario and we saw how we can solve each scenario, whether it was packet loss, packet corruption, issue with this issue with the acknowledgements that are not getting sent because those could be lost as well. We talked about the time and utilization. So it's basically a process of us facing a problem and how we can specifically solve that problem. So lastly, what we have discussed is we have discussed the performance and the utilization. And I think we covered the go back and end as a technique, but I'm gonna recover it and then we're gonna keep going to the next mechanism, which is selective repeat. And we'll talk about the difference, then we will dive into TCP. So that is the plan. Okay. Does anyone have any questions before we begin? Nothing? Okay. So, as usual, the lecture is being recorded and some of the slides are being used or utilized from the book. So, and there's a direct link to the book if you're interested. So, the roadmap for the transport layer or the objectives of this slide specifically as I said in the last lecture, we talked about the reliable data protocol itself. We have not yet spoke about TCP itself. TCP will include all the methods that we have discussed in the prior lectures, and we will see how TCP actually works. So by the end of this lecture, what I hope is that I'm going to explain how TCP is and ensure reliable data using acknowledgement and transmissions. You're going to be able to describe how flow control happens and prevents buffering between sender and receiver. We're also going to talk about the handshakes, a two-way handshake, a three-way handshake, and we're going to see what is TCP using and why are we using a three-way handshake. We'll talk about TCP, how it closes connection, and we'll give some human analogies of the handshake and various cool things, okay? So that is that. So the next couple of slides from here, probably to another 6, 7 slides, we're still in the principle of reliable data transfer. We have not yet moved on to TCP, okay? So go back and send is we introduced a pipelining so we can fix the problem of the stop and wait inefficiency that we saw. Because we saw that in the last lecture that the sender is not getting utilized as much. They're only sending the packet and it's going idle. So we're looking at a protocol that implements the pipeline go back and send. And we said that with the go back and send, the sender has a window size, and each packet carries a sequence number, as we discussed within the packets. And in this diagram that we see here, we have various colors or various segments or clusters in this window size, such that the already acknowledged are the greens. That means the packet has been sent and has gotten an acknowledgement from the receiver. The yellow is in flight, it has been sent but has not been acknowledged. And usable is not yet seen because as we get an acknowledgement from yellow, then it moves a window size n+1, so it moves to the next packet. And the not usable is have not been yet sent or even acknowledged. And we said the acknowledgements are cumulative. That means all packets up to sequence number n have been received. And then when we get a sender acknowledgement, it slides the window forward to n+1. So the sender runs a timer for the oldest acknowledged packet, and we said that there is the timer is helping us with various things. It is helping us with retransmission. It is helping us with packet loss, out of order packets, packets that are corrupted. This timer is basically something for us that we set to make sure that, hey, within this time frame, if we did not receive an acknowledgement or we did not receive the specific packet in order, then we can go ahead and reinitiate the idea of sending it back. So that is that. So that is the go back N that we discussed in the last slide. The reason I'm coming back to it again is because the selective method builds on top of this. So the go back and receiver is very much simpler to go back and N from a sender perspective. The receiver is that it always acknowledges the highest in order packet that has received so far, so the first packet that has received. And we said that if an out of and this basically we're going to have also kind of like a visual of the sender, and it is very simpler quite to the sender. The receiver is much simpler. So if we receive an out of packet order, the receiver will discard it. It will not buffer it. So if we sent packet 1 and we sent packet 2 and we sent packet 3, but there's an issue with packet 3, the receiver will send back packet 1 and 2, but it will discard 3 and also discard 4 until it resolves packet 3 itself. So in the diagram that we see here, RCV base marks the next expected sequence number of packets. So packets before RCV base are already acknowledged in red, and then packets after or maybe out of order in pink or have not been received are in gray. So the receiver doesn't really need to do much. It just tracks that, hey, I received this specific packet. I just need to send this one back for me to accept or acknowledge the next one. And then this is an action version of the go back and end with a window size of 4. This is to show you how this specifically works. So at time 0, we have a sender and receiver as usual, and we have a window size of n4. So the sender is sending 4 packets. So here in this scenario, packets 0 and 1 are received, and acknowledgement is being sent back to these. Packet 3 arrives out of order. Packet 2 is lost here in this image. So packet 3 arrives and it's out of order. So it gets discarded because we have to deal with packet 2 to move on to packet 3. So as we said, acknowledge 0 for packet 0 goes back, and acknowledgement 1 for packet 1 also goes back. And duplicate acknowledgement is also propagating to the sender because we have not received an acknowledgement for packet 2. So the sender 3 receive acknowledgement 0, and they would up the n size by 1. So it wants to send packet 4, but we know that it is discarded. The receiver would say, hey, I received packet 4 from you, but I still need to go back and resend packet 2 because it has been lost. And then we get an acknowledgement for the 4th packet, or the second packet, and then we do an increment of n+1, so we try to send packet 5, and it also gets discarded because we want to send packet 2 that has been lost. So sender now sees there's another duplicate one. The duplication that comes in as an acknowledgement, it indicates that, hey, there's something going on. Why would there be a duplication? Is to give like a ping or to give some sort of initiation that something has been going on. So receiver gets packet 4 and 5. Since packet 2 is still missing, as we said, both are being discarded. So the receiver keeps sending duplicates acknowledgement 1, acknowledging the last in order packet that was sent. Then eventually the sender itself will have a specific timeout, and this time will expire for packet 2. So then the sender would say, hey, the time has expired and I have not received an acknowledgement. Let me go back and resend it. So then it goes and back sends 2, 3, 4, and 5. The reason it sends 2 is because we said 2 has not been received yet, and 3 and 4 and 5 are the next in order packets to be sent out. So now the receiver gets all these packets and they are delivered to the application, and they do send an acknowledgement back. So that is the full go back and end cycle. We see packet lots leads to discarding out of order packets, and retransmission happens after the timeout has been done. So does everyone understands the go back and end? Okay. So now we're gonna move to the selective protocol. So in the go back and end, when a packet is lost, the receiver would discard the out of order packets, and the sender retransmits the lost packet plus all the later ones. So that is simple, and that is very nice, but it's insufficient because there's a lot of retransmission that is happening between the sender and receiver. So we need to find a way to improve on top of this. How can we do that? Is by using the selective repeat. So with the selective repeat is that the receiver sends an individual acknowledgement for each correct received packet. It can buffer out of the order packets until the missing ones arrive. So when we send other packets that are out of order, we don't just discard them. We hold them in a buffer such that we don't need to do the retransmission for them again, whether it's the sender or receiver. The sender acts as a separate timer for each acknowledged packets, so only the missing packet is retransmitted when the time expires. So packets are sent, there's some sort of corruption. We hold these packets in the buffer and we retransmit them only when the time expires. In the original method that we had with go back and end, the time expires, then we do transmission, initial transmission like again, and then it has to be sent back. So in that way, we are utilizing and being more efficient. For the sender, it still has this window size of n, so it controls how many packets can be outstanding, but acknowledgements move independently. So unlike go back and end, selective repeats avoids unnecessary retransmission and makes more efficient use of the channel. So let's see how a closer look of how the selective repeat happens from a sender and receiver window. On the top, we have a sender view. So, and we have our window size. We have green packets that are already acknowledged. We have yellow packets that are waiting to be acknowledged. They are sent, but are currently in a waiting phase. Blue has not been initiated yet or are sent yet. And then everything else outside the window size is we can just like discard it in the essence that we're talking about this specific protocol. At the bottom, we have the blue, which is the correctly received and in order packets. Pink are out of order, but they are buffered here. They're out of order, and they are buffered but already acknowledged. And then we have the black arrow or the ICV base. It points to the next expected packet. This highlights which is the next packet that is supposed to be sent in order. And the window shows which sequence number are acceptable. So So that is the key point. Unlike go back and in, the receiver can accept and buffer out of order packets. This allows the sender to retransmit only what is missing rather than sending everything else after a loss. So if we send 4 packets, the second packet get lost, and we also send 3 and 4, we hold these 3 and 4 until the second packet is dealt with, and then we go back to the usual process that it is, how it usually is. So the selective repeat is going to be more efficient, but also going to require us more states. It's going to require us more buffer, also multiple timers, and we need a way to track the acknowledgements that are happening. So everything comes with its pros and cons, because the initial way we did not need a buffer, really, with the go back and end, but the retransmission is happening a lot. So now you got the big picture of how the selective works. This is just a way for us to define the formal rules from the sender and receiver. So the sender, when data comes down from above, if the sequence number is within the window, the sender will go ahead and say, hey, this packet is ready to be sent. If we are on a timeout for packet N, we only resend packet N and then we restart the timer. On receiving acknowledgement for the sender, we also mark packet N as acknowledged. If it was the smallest unacknowledged packet, we slide the window forward. So that is the idea. It is basically once we receive a packet and it's acknowledged, the window size moves up by 1. Now for the receiver, if a packet N is in the receive window, it will send an acknowledgement back for N. If it's out of order, we will buffer it. If it's in order, we deliver it and also release any buffered packets that is now fit in order, depending on the order of the packets, obviously. And if the M packet to the left of the window has already been acknowledged, then we send another acknowledgement in case the earlier one was lost. Otherwise, we would just ignore it. Does that make sense? Anyone has any questions? Okay. Let's look at the selective repeat in action now with a sender and a receiver. And we also have a window size of N, which is equal to 4. So we assume that the sender is sending 4 packets and packet 0, packet 1. Initially, packet 0 here is packet 1. So packet 1 and 2 is sent and is being received. Packet 3 is lost, but we receive packet 3. We don't discard it. We buffer it, and we send an acknowledgement for packet 3. So and then when the first packet comes back, we increase the window size by 1, and and then it would receive packet 4 and say, hey, this is still out of order. We still need to deal with packet 2 in the image, but it's essentially packet 3. We still need to deal with that before we deal with packet 4. So we buffer it. And then the window size would increase after packet 2 gets sent back. We go to 5. It's also out of order, so we also buffer it. And then the record has arrived for acknowledgement 3. So then what we go back is that the time it has run out. And then we would only have one way of transmission to send packet 2 again, because packet 4 and 5 and 3 are already in the buffer. So it would just go back and deliver these, but it has to deal with packet 2 first. So that is the difference between them, the selective repeat and then the go back and in protocol. So back to the roadmap of our chapter, the transport layer. We covered all the top ones that are mentioned. So we covered transport layer as a service, covered multiplexing and demultiplexing. We also covered connectionless UDP transport, and we talked about the principles of reliable data transfer. Now we will dive into TCP. So This is the actual protocol that we are using, and then we're going to implement the ideas we have been discussing and see them in practice. So initially we have the RFCs that is typical for every protocol, and they are listed on the top. And you can go back and refer to those, and this is a way that we have some sort of documentations for each protocol for us to go back to see the formal way of communication, the formal rules that are existing. When we talk about TCP, it is a point-to-point. That means exactly there's only one sender and one receiver. We also said it provides reliable and ordered byte stream, so data can arrive exactly as it's sent. This is different from UDP, which is only message oriented, so it does not guarantee reliability or order of the data. Also, TCP is not half duplex, it is full duplex, meaning that data can be sent or flowed in a bidirectional way at the same time. And the MSS we have here is the maximum segment size. This defines the largest packet or the largest data or payload that a segment can be carried out. And that is depending on the initial connection that we have with the sender and receiver. I will discuss and we'll talk more about this as we get to the handshake process. Also, we said TCP uses cumulative acknowledgements, like go back and end to confirm the received data. It also has a pipeline protocol that allows multiple segments to be sent out before waiting for acknowledgements. And we said it's connection oriented. That means there's some sort of initiation of connection, like a handshake, before data is being exchanged between the sender and receiver. And also it is flow controlled, so the sender doesn't overwhelm the receiver with the buffer. And we will see how that happens. How do we make sure that the receiver doesn't get overwhelmed from the sender? So these are the primary ideas that we will discuss with TCP, and we will talk about more of these in depth. So let's look at the structure again. This is very important for the TCP segment. We want to understand why they exist, and we want to see what specific fields are included in the structure itself. So each field connects back to the reliable data transfer principles that we have already learned. So the first thing is that the source port and destination port, this is used for multiplexing and demultiplexing. This is also included in UDP. But we said that UDP does not use the IP address, it just uses the port numbers. We also have the sequence number. This is identifies where each byte of data fits in the overall byte stream. We also have an acknowledgement number. It is also 32 bits. This tells the sender the next byte by the receiver expects. At the bottom here, we do have the application data. This is the data that we are dealing with, or we're requesting from the application, whether it's a web page or you're requesting a picture, a video image, that is the payload or the data that is being sent. We also have an internet checksum, and this is just like UDP. It is a way of detecting errors in the header and data. So that is also included in TCP as well. Okay. And then we have extra features. We have like the TCP option. This allows for like extra features or variable in length depending on which options are being used here. And then because of that, we have a TCP includes a header length to tell how long the header actually is. That was that one. This was the header length of the TCP that tells the header length. I skipped a transition. And we have the RST, SYN, and the FIN. These are the flags. Those are used for connection management. We're going to study these with the handshake. And we have the receive window. This is used for flow control. This tells the sender, hey, this is what I can receive. And it tells the sender how many bytes it's willing to accept. Then we have the C and E. These are used for congestion. Obviously, we will not discuss this In this lecture, we will talk about congestion at a different lecture. But that is the idea, and the use for it is for congestion. And then finally, this is not really used a lot. It is the urgent data pointer. It's a field that exists, but really not in practice a lot today. And it was only the reason it was formed is that it was for applications that needed an urgent or priority data. But most modern protocols no longer rely on it, but it do exist as a field. Okay, so let's talk about the sequence number for TCP and what it represents. So we need to remember that TCP views all data as one continuous byte stream. So there is no really no separate packets. We talked about the idea of packets to make it clear for how the protocol works. But here each byte is streamed in number, and these numbered is what allows the TCP to resemble the data in order and on the receiving side as well. So the figure shows here that we have is the sender sequence number space, and every byte that can be sent is going to be assigned a unique number. And then we can see here the window is divided into segments. And these regions or segments is that we have the green bytes. These are already bytes that have been sent and acknowledged. The yellow ones are going to be bytes that have been sent but not have yet been acknowledged. And we also have the blue is usable but not yet sent, depending on the window size. And the gray is going to be not usable. So they're outside of the window. So that kind of gives you a visual sense of TCP sequence number as a visual. So going back to our structure of this segment is that here we can see the sequence number inside the header. This number lets the receiver know exactly where each piece of data fits within the byte stream. And then the window size represents the number of byte streams, obviously, that we have here before needing an acknowledgement. And then we also have an acknowledgement number. This is the field that tells the sender the next byte has been received. And then it can move on to the next byte depending on the acknowledgement that is sent back. And we said the acknowledgements are cumulative, meaning everything up to that byte number has been received successfully. So one acknowledgement can confirm multiple bytes at once. A common question that we would have with here is that what if segments arrive out of order? So like what happens if those specific segments that we are sending arrive out of order? The TCP specification doesn't really define something or a single rule for that. It is up to the implementer or the developer or the application user, the application developer itself. So some system may buffer the out of order data, others may discard it and wait for a transmission. That is depending on the selective process that we have or the go back and end. So we have dealt with that and we've seen what the two ways to deal with that. So let's look at a simple example of TCP in action and see how sequence numbers and acknowledgements go hand to hand, how they work together. We have an example here of a simple telnet scenario from host A and B. And the idea is that host A is going to send a character to B and B is going to echo it back. This is kind of similar to the ICMP protocol, but each transmission is going to involve a TCP segment with a sequence number and an acknowledgement number. So we're going to see how those work together. Okay. So notice that here host A would send the data with a specific sequence number, and it's going to be 42. And the acknowledgement that is being sent back from host B is going to be acknowledgement 43. So that is one more than what the original sequence number is. This tells like, hey, host A, I have received everything up to byte 42. Next, I'm expecting byte 43. Similarly, when host B sends data with a specific sequence number, which is we have this one is 43 and it sends back the increment of 43. Here is that when host B sends a specific sequence number that is going to be 79, it would go back and increment it with 1. So the idea gets repeated here. So the sequence is what is getting sent. The acknowledgement is an increment of that original sequence. So it is always the acknowledgement and the sequence go hand to hand, and the TCP always acknowledges the next expected byte. So it makes it a kind of an easy way for us to track and see a reliable way for us to track and have some sort of way such that we can ensure order delivery is happening or being implemented. And here we see C, and C is going to be sent back. That is the payload itself. So user type C, ping tells P, and then P would echo C back to it. So that is the example. So that is the scenario. Is that understood? Clear? Okay. So we've seen the sequence numbers and we've seen the acknowledgements to keep track of reliable data transfer. But there's a slight issue that we have not covered is that, or not discussed, is how do the TCP sets its timeout values? Is it randomly set? How did they configure these specific timeout values? And we said the timeout values control how long a TCP waits before assuming a segment was lost with retransmission. So we have a timer that tells us, hey, when this runs out, we need retransmission to be resent. The packet needs to be resent, or the data needs to be resent. And also this time depends on the round time trip as well. The round time is from sending a segment until receiving an acknowledgement. So the problem is that we have here, if we set the time too short, it might retransmit too early. When the segment isn't really lost, could be not lost, but the time that we have set is very short. If we do it too long, that would be unnecessary transmissions and a waste of network bandwidth. On the other hand, if we do set it too long, then TCP will react very slowly to actual losses and delaying. So the question that we ask ourselves is, how do we determine or how do we estimate the round time trip? And the way it does that, TCP, it measures a sample round time. This is the starting timer from a segment is sent and stopping it when the acknowledgement is received. It is important to ignore retransmitted segments here for this measurement. So we don't get the distorted time. We just want the actual time from when the packet was sent and when it was acknowledged. However, sample RTT, sample round time trip, it will vary. It can vary because there's a lot from one measurement to the next, depending on the network congestion or the next or the routing itself. So one way for us to send is not going to give us the ideal or the optimal time that we have to set as a timer. So we need to send it multiple times and find a way to take the average. So we take the average of the several recent samples, not just the recent one. It's going to help us with the timeouts to adapt more gradually instead of jumping from one measurement to another. So that is how we can estimate the runtime trip. This shows, I don't want you to really worry about the formula here. I just want you to understand how this happens. This shows how the TCP recomputes the estimated runtime trip every time it gets a sample. So we have the formula on top. So this means the new estimate is a blend of the previous estimate and the most recent sample. So the parameter that we have here, alpha, determines how much weight we give it to the new measurement versus the past. And this is the process that is called also as EWMA, or exponential weighted moving average. So this helps us smooth out variations so that older samples have less influence over time, and while new ones have more influence. So the typical value they found is that for alpha and most TCP implementations is 0.125 or 1/8. And here the graph below shows how they did this in practice and how this was plotted. So it plots both samples, the sample RTT and the estimated RTT that measures between a host. And the host that they have here is the University of Massachusetts and a host that is located in France. So we notice the blue line, basically it's going up and down, so it fluctuates a lot. While the pink one is the estimated moves out very smoothly. So that is the benefit of having like exponential weighting, so that TCP avoids reacting to every small spike that could be congestion, delay, and it makes it more stable overall. And then that is for the estimated time, round time trip. How do we set the time interval, the timeout interval? So TCP doesn't just take the estimated round time trip, it would add a safety margin to handle the variations in the network delay. So the idea is that here, if the RTT samples are jumping around, TCP should wait a little longer before assuming a packet is lost. So this is the timeout that we have when a packet is lost or corrupted or needs to be resent. So the timeout value depends here on the average runtime trip and how much it varies over time. So here I just want to deliver the idea. TCP sets the timeout as the estimated runtime trip plus some extra buffer. And if the runtime trip here varies a lot, then the buffer or margin grows bigger, giving the network more breathing room. And here what we have is the variation is dev runtime trip. This is just simply how much measured runtime trips are deviating from the average. So the formula here isn't exactly important. It's just running an estimate that tracks how bouncy or stable the RTT has been with the different plots that we've seen in the last slide. So in summary, the idea is that overall, when a TCP sees the network delay is getting inconsistent, it automatically stretches the timeout to stay reliable. When things really settle down, it shrinks the time back. So TCP would be adapting in real time. So it stays cautious when the network is really unstable, has delay, has in control, and reacts faster when the conditions are more steady for the faster transmission. We talked about sequence numbers and acknowledgement. Now we want to summarize how the TCP sender behaves. So this is just like a simple high-level idea of what the sender does in response to different events. We're going to go through a series of events. We're going to see how it reacts. And the events that we're going to see here is going to be events that we already have discussed in the reliable data protocol itself. So we have the first event, data is received from the application. So when the data arrives from the application down to the transport layer, TCP would take it, it would make a segment and it would assign it a sequence number. That is the byte stream number of the first byte that in the segment. Then the TCP would start a timer, but only if one isn't already running, depending on which sequence we are currently at. Then we have event 2. This is going to be the event of a timeout. So if a timeout occurs, TCP was going to say, hey, timeout has run. I would retransmit the segment because I have not received an acknowledgement. So this would get triggered only if an acknowledgement has not been sent back. Then then it would restart the timer on the given next sequence. So this is like very basic self-correcting behavior of TCP that would expect a packet is lost. And our third event is when the acknowledgement is received. When an acknowledgement is received, TCP checks whether it acknowledges any previously unacknowledged data. If it does, the sender would say, hey, it would send updates to now what has been configured and received, and it would restart the timer. And then it would go to the next in-flight packets or the in-flight sequence of bytes, and it would go ahead and send that. So we're going to be jumping between these different 3 events. We're going to send data, react to timeouts, and process the acknowledgements to keep things reliable and efficient. Does that make sense how TCP works from a sender point of view? Okay, so let's look at what happened at the receiver side. And we always said with TCP, the receiver side is very simpler compared to the sender. And it's basically just gonna receive and react. So we're gonna look at different events and gonna see how TCP would react to those. So the first thing that we have is out of order segment. So if an in order segment arrives with the expected sequence number, TCP would say, hey, this checks out. I will send an acknowledgement back. This is a straightforward case. So the data arrives in order. The receiver just confirms it right away. We can have another case where we have an in order segment arrives soon after. So many TCP implementations would wait briefly to combine the acknowledgement into a single commutative acknowledgement. This would help reduce the acknowledgement as a traffic. So it will still confirm the data has been received so far and sends one sort of acknowledgement. If the segment arrives out of order, here we have in the third case or third event, meaning it has a higher sequence number than expected, TCP would say, hey, there's a gap, and it would send a duplicate acknowledgement for the last byte it received. And that should give an indication to the sender that there's something going on. The duplication would say something like, hey, I'm missing something between, please go ahead and resend it. And then finally, if a new segment arrives to fill that gap, the receiver immediately sends a cumulative acknowledgement. Everything now has been received and ordered. So in short, duplicate acknowledgements point out to missing data. Whenever we send back a duplicate acknowledgement, we are trying to say that there's something going on that is wrong. The cumulative acknowledgements confirm that everything now is back in sequence. Okay, so to wrap up TCP reliability, let's look at a few retransmission examples. These will help us illustrate and should give you a visual of how TCP works with different cases. So in the first scenario we have here is lost acknowledgement scenario, is that the host would send a segment, but the acknowledgement is lost on the way back. And we said since TCP never gets the acknowledgement, the timeout would expire and the sender would retransmit the same segment. This is basically, we are just everything that we discussed in the reliable data protocol is getting repeated here. This is the mechanisms that our TCP is using. And we have a timeout that runs out, it would send back the data and then it would be acknowledged the next time it was sent out. In the second scenario that we have here is we have two segments that are being sent, one carrying 8 bytes and another one carrying 20 bytes. They both reach the receiver, but both acknowledgements arrive back. So the sender experiences a premature timeout for the first one. So then the timeout runs out. So the TCP would retransmit the first segment, but since the receiver already has all the data, it responds with a cumulative acknowledgement of confirming everything, converting everything up to byte 120. So the cumulative acknowledgement mechanisms prevents unnecessary retransmission from happening. So we don't need to send retransmission acknowledgement for each byte of data. We can just send it for both. This is last example. We again have two segments being transmitted from host A to B. So the first acknowledgement is lost on its way back, but the second, which is cumulative, arrives successfully. The cumulative acknowledgement that we had in the last slide covers both of the earlier segments and confirmed that all bytes have been received, even though the first acknowledgement was lost. So because of that, the sender knows that both previous segments were delivered correctly and can safely continue to send new data. So it would send it back. So the strength that we look at with TCP is one of it is cumulative acknowledgement and make sure that it's naturally resilient to lost acknowledgement. So if the sender if the sender can still send data without confusion or retransmitting data that is unnecessarily. Before we wrap up TCP, there is a fast retransmit. This is just a way of optimization and a mechanism for us for TCP to recover from lost segments more efficient without waiting for the timeout. So here we don't really focus on the timeout, and it's going to be based on indications. So here we see host A is sending 2 segments to host B. The first one has a sequence of 92, and the second one has a sequence of 100. The second one gets lost somewhere along the path from host A to B. So host B would receive the first segment successfully, but since the next one is missing, it would keep sending acknowledgements back for 100. That means the next byte it is expecting. So each new in order segment that arrives after the loss is going to be stalled to trigger a duplication that we would have. Now, after the sender sends 3 duplications, after the receiver sends 3 duplications back to the sender itself would say, hey, there's 3 acknowledgements. It realizes that there's something has been going on or something has been lost. So the one with the smallest acknowledged sequence number that has going on. So instead of us for waiting until the timer runs out here, TCP already expects what's happening and retransmits the missing data. So this is the way of fast retransmission mechanism. It avoids the timeout and it avoids unnecessary delays and helps maintain the throughput. So it is some sort of way for us to know that, hey, when we're receiving acknowledgement, indicates that for 3 segments, we can say, hey, there's something that is lost most likely. So we retransmit right away. We don't have to wait for the timeout to finish. So as a summary, if the sender gets 3 additional duplicates acknowledgement for the same sequence number, it would just say, hey, I assume that there's something going on, and I would retransmit it right away. So the TCP fast retransmit acts a little bit faster without relying on the timeout that has been set. So it's just way of it's based on detection, based on the 3 segments or the 3 acknowledgement that we have got back with the same sequence number. So we talked about TCP segment structure and reliable data transfer with the acknowledgements and sequence numbers. We looked at a few scenarios of different scenarios that would have different needs. And now we're going to speak about flow control and connection management. So the flow control itself ensures that the sender does not overwhelm the receiver. So it's about matching the data rates. And then connection management is primarily the handshakes that we're going to discuss. And it's going to talk about the connection that would happen between data is getting sent. So we're going to take a closer look into each one. So before we dive in on how TCP works in terms of flow control, you want to understand why it's needed. So the diagram shows here the receiver side, the receiver protocol stack, and we have IP at the bottom, TCP in the middle, and the application is going to be at the top. So the IP layer is responsible for receiving incoming datagrams from the network and passing it up to the TCP. The TCP layer in the middle is responsible for extracting the data and placing it into the buffer that we have. And the application on the top would need or read the data from the buffer at its own pace. So these are together how the receiver protocol stack works. Each one is responsible for something that is specific. So let's see how the flow control happens, where we don't overwhelm the receiver. So when a TCP segment from the network arrives from the network layer, its payload is delivered up to the upper stack, which is the TCP layer. And usually the TCP would place the data into the buffer where it waits for the application to read it. Usually the application would just do a socket read to take the data from the buffer. And just like we discussed in chapter 2 with the socket assignments. But the question here we have to get you thinking of flow control is that what if the network keeps arriving faster than the application can read from the buffer? So we are receiving a lot of data that is being stored in the buffer, but the application is not reading it faster than what is being received. So how do we define a way for us to make sure that everything stays in a flow control way? So if this happens, the receiver buffer would fill up, and this can lead to data that is being lost or transmission that are not getting utilized in a fashion way. So this is why we use flow control, is that we make sure that the sender that is sending the data has a rate of transmission that stays in sync with how quickly the receiver can receive or process the data. So it has to be kind of synced. A quick way of an analogy to think about it is the flow control before diving into the details is we want to know the same question remains is that what happens if data comes faster than it can be handled? So the human analogy here we have is that no one wants to drink from a fire hose. So meaning that if the water rushes out too fast, you cannot really swallow it. You will end up choking or spilling it everywhere. In TCP, it is the same idea that is being implemented. The network layer would deliver up to the TCP buffer, but if the application can remove the data fast enough, then the buffer fills up and data would be lost. So that's like the receiver getting blasted with a lot of information that it cannot really process. So that is to give you a human analogy of why we use flow control, or why does TCP make sure that the sender turns down like the hose here and sends data at a rate that the receiver can actually handle. Here in the analogy of the water, it's very fast, so it needs to be like but fire hose, I don't think you can control the power of them. No, they do send at a speed time. So yes. So now we've seen the problem with the flow control. And so let's see what flow control actually does in TCP. So flow control is the receiver way of protecting itself, basically, from being overwhelmed by the sender. And simple terms we have, this receiver would be the one in control. It would say, hey, the sender send the data at a specific pace and how much data can be sent at a time. That is the way so we can prevent buffer overflow that would happen. So let's see how TCP implements flow control. The idea is going to be pretty straightforward and very easy. Here we have the figure on the right-hand side, and we said that the receiver tells the sender how much free space in the buffer it currently has. So that is done with RWND, and this is basically the receive window. This is the free buffer size that we have. And the total received buffer size is called RCV buffer. This is which can be set by the system or adjusted by automatically by the operating system. So the receive window value would reflect how much data in the buffer is still free. It decreases as the new data fills up to the buffer and increases as the application reads the data. So an application is getting read, more space is getting freed, more data is being stored, and it gets repeated in that cycle. On the sender side, TCP also uses the RWND to value the limit of amount of unacknowledged in-flight data. That data can be sent at a given time. So the sender won't send more data than the receiver advertised windows allows. So that's how overflow is prevented on both sides. So this idea of flow control guarantees that the buffer never fills up faster than the data that is being arriving. So TCP flow control is a receiver-driven mechanism. The receiver is saying here is how much data you can send and how much data I can handle right now. Does that make sense how that works with the flow control? Okay. So this just highlights the receive window. We talked about the structure or the data labels inside the TCP segment format. And the receive window is the one that is responsible. This is going to advertise the available buffer using the receive window value or the RWND value. And we said this is dynamically changed based on the data that is being read from the application, and then it frees out more when the data is being read, so we can store more data. So that is how it works in practice. Now we will dive into connection management. So we understand flow control, right? Does anyone have questions about that? Flow control, how can we manage? Now with connection management, when we talk about connection management, you can just directly think of the handshake. There's going to be a way of connection that needs to happen before we can actually talk. So maybe that is, I can get your attention first before I speak to you. I don't want to speak to you and then my attention is not there. So I might say, hey, or I might make eye contact with you for us to communicate with each other. So the idea is still here in TCP. They need to agree on certain parameters, like their initial sequence and buffer size, so they can stay synchronized once data begins transferring. Here we have on the left is the client, and on the right-hand side, we have the server. So on the left, you see the client creating a socket connection to the server using the host name and port number. This is something related to the programming assignment that we have did. On the right, the server is going to be listening and accepting connections. So once it does, it both establishes a shared state variables like a sequence number and the buffer size for flow control. So in short, the handshake is a way for us to define rules before the session initiates. And this is a way of TCP making sure that both sides are in sync before actual data is being sent. So let's look at the handshake process step by step. We know TCP uses a three-way handshake. We are going to start with two and see what the problem of having a two-way handshake. So here we have another human analogy between Alice and Bob. Alice says, let's talk. Bob replies with, it's okay, let's talk. So that is a two-way handshake. Both think that the connection is ready. In networking, it would be the same idea. It would be like the client is sending a request and the server acknowledges it. But that is not sufficient in a two-way handshake. And here's why. So the question we ask ourselves is would this always work over a real network? That's going to be not possible. And not necessarily because there's going to be variable delays. We have messages losses, we have reordering, and the second message could get lost or duplicated, like similar to the acknowledgement that we discussed. And we know that with the sender and receiver, they actually cannot see each other. They have a way of communication. So we don't know if the connection is lost or is still connected, it leads to confusion. So the two-way method works for humans, but not for unreliable networks. So that's why we use a three-way handshake instead to make sure both sides agree and are synchronized before any data is being exchanged. So now that we have introduced the idea of two-way handshake, let's walk how this works in a simple case. So the client that we have, we also have a client and a server. Usually the client would choose an initial sequence. We can say X here that you can see on top and sends a connection request to the server. The server would establish the connection, it would receive it and would reply, and then both states are in a connection established state. So connection is happening. But then the client would send its data, which is X plus 1, for which the server acknowledges and everything works as planned. So in this example, there's no problem at all. We are taking the best case scenario or the base case. So both sides agree, data is exchanged, and the connection is closed. But we know that this is the best case scenario, so things won't always go this smoothly. Yeah, we introduce errors, retransmissions, delays, packet loss, packet corruption, out of order. So this is where it's gonna get interesting. So let's take a look when things don't go perfectly. So the client sends a connection to the server, and both sides have the sender send an acknowledgement or a request a connection. Server would say, "Hey, I'm ready to talk," and connection happens between both sides. So that is good so far. Let's see where the wrong happens or where the fault happens. So we suppose the client, let's suppose that the client doesn't hear back and assumes the message was lost. So it would retransmit the same request and that is usually normal because TCP would try again if it thinks it got dropped. The server receives the duplicate request after the first initial connection already, and it would treat it as a new connection. It doesn't know that that is part of the old connection that we had. So it would respond with an acknowledgement and moves to the new established states. The problem that we have here is that the client is already gone. So now the server thinks that there's an open connection, but the client isn't actually there. So this is what we called a half open connection. There is no client, and this is a problem. This is a way for us we have to deal with. So let's take a look at another issue that can happen with a two-way handshake. So the client starts as usual, sends a connection request for a sequence number, and the server acknowledges, and both sides enter the established states, and client sends some data, and everything looks fine. But here we suppose the client didn't get an acknowledgement. Maybe it was lost, so it retransmits the request again. Then, not hearing back enough, the client would also retransmit the data. Meanwhile, the server had already closed the previous connection and forgotten the initial states. So now the old retransmitted data arrives to the server, but the server says, "Hey, this is a new data," or "This is a new connection." It does not know that this is coming from the older states. That means the server can accept and process duplicate data that shouldn't have been accepted at all. And that is a waste of bandwidth and a waste of also time. So that is another major flaw with the handshake that we have. It could cause duplicate or invalid data delivery. So now we're going to look at the actual TCP handshake that it's using and how it fixes these problems that we have discussed with the two-way handshake. So the first thing as usual is that both client and server starts by creating a TCP sockets and entering the listen states. Here the sender or the client would initiate a connection by sending a send message, and this includes the initial sequence number X. The server would receive the acknowledgement state and replies with send plus acknowledge. This means it acknowledges the client original request and also sent its own initial sequence number Y. And then finally, the client sends back an acknowledgement acknowledging the server itself. So every request that is happening between the server and the client needs to be acknowledged, whether it's a connection-based or data-based. At this point, both sides are ready to communicate and the connection is fully open to data transfer. So the extra step that we have is the final acknowledgement is what prevents the earlier problems that we had. So it ensures that both sides are synchronized and eliminates issues like half open or duplicate connections. Does that make sense how TCP works with the three-way handshake? Okay. Here's a human analogy, obviously, to give you the idea of outside of TCP. Does anyone does this sort of climbing before? Has anyone tried it? No? Okay. So yeah. So a real life example of rock climbing here is that when you're about to start, the climber asks on belay. That's like saying, "Hey, are you ready to establish a connection?" The belayer would say, "Hey, belay on." That's saying, "Yes, I am here and ready. I acknowledge your request." And then the client will go back and say, hey, I'm gonna start climbing, confirming that we have received, confirming they have received the acknowledgement, and they're ready to begin. And that is the three-way handshake. It is clear, reliable way before it gets sent. Thank you, Ian. Yeah, that is an analogy. I try to involve these analogies a little bit outside the in-depth material that we discussed to give you for you to understand the concept. So it's going to be just like in climbing, both sides confirm readiness, so no one ends up hanging midair, or in TCP case, mid connection. So closing TCP connection is the last phase for us after we do what we need to do. And like a good conversation that we have always ends. So TCP connection eventually comes to an end as well. When either side, client or server, is ready to close, it sends a fin message. And this is something that you've seen in your programming assignment. When you're done, you initiate some sort of input that gives an acknowledgement that I am done sending data. The other side responds with an acknowledgement to confirm that it has received the fin. And sometimes it can send its own data at the same time. This can happen maybe live or at the same time. So both sides independently close their half of their connection, ensuring that the data is delivered before fully shutting down. So even with the closing connection, there is an acknowledgement that's happening. That is why that TCP is a more reliable protocol and very useful. So that is TCP in a nutshell: a reliable setup, careful data flow, and graceful goodbye. So hopefully this is very easy. You might say, why we haven't just went into TCP directly and just explained it? Why did we talk about the reliable data protocol itself? Because we've seen with the reliable data protocol, there's a lot of things that we have dealt with, and a lot of mechanisms, a lot of ideas, methodologies that have been exposed to us that TCP uses. So here, when we talk about TCP, that's why it's very short and compared into what we have discussed in the previous lectures. So to wrap up the transport layer, we have two more things to talk about. We need to talk about principle of congestion control and TCP congestion control. Those are the last two things that we need to discuss. So it's going to be the same idea that we talked about: principles of reliable data transfer. I think okay. Yeah, we talked about the principle of reliable data transfer. Then we talked about TCP. We need to talk about the principles of congestion control and TCP congestion control. So that is that. There is nothing that I have. Does anyone have any questions? If you don't have any questions, I'll see you on Wednesday and we'll talk about congestion control. Okay.
Well, it's the best resource.